Welcome all of you. The first topic that we are doing, and this is the first lecture on the first topic. The name of the topic is assignment problem. Now, what is an assignment problem? Assignment problem is one where we are assigning or allocating resources to uses. That means I have n number of resources, n1, n2, n3, and I have n number of resources. Again, against that I have n number of uses, again n1, n2, n3. In other words, for example, the first problem that we'll be solving is assigning 5 salesmen to 5 districts. The important thing here is the number of salesmen is 5 and number of districts is also 5. With the condition that one salesman can be assigned to only one district. That means typically an assignment problem is 1:1 allocation of resources. Okay. Now this assignment problem algorithm is primarily an algorithm for minimization. So can it be used for a maximization problem? The answer is yes. It can be used with some modification. Okay. Now there are various steps. Now the important difference between assignment problem and transportation problem is transportation problem is not 1:1 allocation. There can be one use and there can be more resources. So one resource can be assigned to more than one uses, or one use may have more than one resources attached to it. So it is not necessarily a 1:1 allocation, whereas in transportation problem, it is 1:1 allocation, one resource, one use. You cannot have one resource allocated to more than one uses, and you cannot have more than one use allocated to more than one resources. Fine. So now this problem, if you see, this is the first problem in your book as well, that will be giving to you. These are 5 salesmen S1 to S5. Their names are S1 to S5. And these are 5 districts D1 to D5 where they can be allocated. With the condition, of course, that one salesman will be allocated to only one district. What are the numbers in the matrix? The numbers in the matrix are cells in 1000 rupees. That means, in other words, if salesman S1 is assigned to district D1, the cells which will materialize or the salesman will be able to do is rupees 40,000. Okay. Now what is the objective of this? To assign the salesman to various districts in order to maximize the sales, and therefore I am calling it the maximization matrix. What is our objective? Assign the salesman to districts in such a way that the total sales are maximized. Fine. Now 5 salesmen, 5 districts. So it's a balance problem. The number of resources is equal to number of uses. So it's a balance problem. It's a maximization problem where the sales are required to be maximized. What are the steps, therefore, in assignment problem algorithm? Now coming here, if you see, these are the steps. Algorithm is nothing but the steps as I explained in the previous lecture. Pre-checks. There are 2 pre-checks. 2 pre-checks are with the objective of making the problem a solvable problem. Okay. First check. Is it a minimization problem? If it is not a minimization problem, if it's a minimization problem, no issues, go ahead, ask the next question. But if it is not a minimization problem, convert it into minimization problem. Okay, this will do. Next step, is it a balance problem? When is a balance problem? When we call a problem a balance, when the number of resources is equal to number of uses, 5 salesmen, 5 districts, so we call it a balance problem. Number of resources is equal to number of districts. So these are pre-checks. So before applying the algorithm for assignment problem, we must do the pre-check. Fine. So pre-check number 1. Is it a minimization problem? Now this is not a minimization problem. The given problem is a maximization problem. Fine. The sales are required to be maximized. Now see, what are the things that we maximize in life? We maximize satisfaction. We maximize sales. We maximize profit, and so on. Now, what are the things that we minimize? We minimize cost, we minimize the time taken to do a job, we minimize wastages, and so on. So, looking at the problem, we should be able to make a guess as to whether this is a maximization problem or a minimization problem. Obviously, the given problem here is for maximization, so it fails my first check. Is it a minimization problem? The answer is no, it is not a minimization problem. It's a maximization problem because the sales are required to be maximized. So pre-check number 1 has failed. So what do we do? Fine. These are pre-checks. Remember, we have not got the problem in a solvable form still. And therefore, the objective of pre-checks is to get a problem in the solvable form. Okay. So firstly, this is not a minimization problem. This is a maximization problem. How to convert it into minimization problem is what we'll see. Now look at this matrix. The maximum sales which I can make out from this matrix is 49,000 rupees. Zeros are omitted, so I'll say 49. Fine. Now 49,000 rupees is the maximum sale which can be achieved at two places, S1, D3. For example, if salesman S1 is assigned to district D3, the resulting sales would be 49,000. So I would love to make an assignment of salesman S1 with district D3. Another possibility is salesman S3 with D4. Another 49. I would like to make an assignment here if my objective is to have maximum sales. Obviously, I will try to make these assignments, at least one of them. If it is not possible to make two, fine. So the process of conversion of a maximization problem into a minimization problem is very, very straightforward and simple. Firstly, examine the maximization problem. Find out the highest number. The highest numbers which I have marked here are 49, either this 49 or this 49. Fine. So this problem is now to be converted into minimization problem. In other words, I must create another matrix which becomes a solvable problem, where the maximum number here will correspond to the minimum number here, and the minimum number here will correspond to the maximum number here. Now what is the minimum number here? 29. The lowest sales are 29. The highest sales are 49, either here or here. So these maximum numbers must become the minimum numbers there, and this minimum number must become the maximum numbers in the new matrix. The procedure is extremely simple. Find out the maximum number. 49 is the maximum number. Fine. So I mark it. I mark this 49, or for that matter this 49. Now 49 has been marked. What do we do? Subtract all the numbers of the matrix from 49. Okay. For example, 49 minus 40 is 9. 49 minus 48 is 1. 49 minus 49 is 0. 49 minus 30 is 19. 49 minus 37 is 12. So first row has been converted. Similarly, the second row. The numbers here are like this. Subtract all of them from 49. So 49 minus 46, 3. 49 minus 32, 17. 49 minus 35, 14. 49 minus 46, 3. 49 minus 41, 8. Second row converted. Third row, same procedure. Third row, 49 minus 48, 1. 49 minus 36, 13. 49 minus 41, 8. 49 minus 49, 0. 49 minus 48, 1. So third row converted. Similar treatment for fourth and fifth row. As you will see, you will get this matrix after converting into minimization problem. Which means that solving this problem for maximization is as good as solving this problem for minimization. Which means that we are not going to solve this problem, we are going to solve this problem. And the solution to this problem will be obtained through solution to this problem. So first pre-check, is it a minimization problem? It failed. So we said convert it into minimization. We did that. We got the minimization matrix in hand. Now we are going to solve this modified problem. Next step, is it a balanced problem? Now, in case of a balanced or an unbalanced problem, what we really mean is, are the number of resources equal to number of uses? Yes, here, because there are 5 rows and 5 columns. If I call these 5 rows as resources and 5 columns as uses, the number of resources and number of uses is exactly 5. So we got 5 by 5 matrix. Is it a balanced problem? The answer is yes. So the second pre-check is successful. First pre-check failed, second pre-check was successful, therefore both the pre-checks have been done. Now comes a stage when we can solve the problem. So we have, after the pre-check, the purpose of pre-check is what? To get the problem in a form which can be solved. Now see, for example, another problem could be, it may be a minimization problem to start with, but it may not be balanced. Another possibility. Third possibility, a problem may not be minimization, it may not be balanced, so both the pre-checks will fail. Here one pre-check failed, one pre-check was successful. Fine. So after doing these pre-checks, then start the steps for assignment problem algorithm. Fine. Now this is my assignment problem which I am going to solve. Maximization problem converted to minimization problem for the, because why did we do this? Because assignment problem algorithm is primarily only for solving a minimization problem. Fine. Great. Now this is the new matrix. What are the steps of assignment? Now start the steps of assignment problem algorithm. First two were pre-checks. For every problem, we'll be doing these pre-checks. Once both the pre-checks have been successful or unsuccessful, we'll deal with them, make them successful, and then go to the steps of assignment problem. Now, assignment problem algorithm starts here. First step, subtract row minimum. Now see, why do we do this? How many ways can we assign 5 salesmen to 5 districts? There are a number of ways in which we can assign 5 salesmen to 5 districts. For example, when I assign the first salesman, I can assign him in any one of the 5 ways. So one salesman is fixed. Next salesman, there are 4 districts remaining, so I'll be able to assign him in 4 different ways. Then next salesman, I'm going to assign him in 3 different ways. Next salesman, I'm going to assign him in 2 different ways. Now see, this is how much? 5 into 4, 20, 20 into 3, 60. Sorry, 20 into 3, 6, 20, 20 into 3, 60, 60 into 2, 120. There are 120 ways of assigning 5 salesmen to 5 districts. One of them is going to give us the maximum sales. And which one is it? One foolish way would be to try all the 120 ways. Amount of time required, not known. And therefore, this algorithm has to be something which will cut down the amount of labor involved. And therefore, we'll be following steps of assignment problem in such a way that we'll directly arrive at the solution. We'll be directly able to get, this is the maximum sale which is possible. So how to do it? First step, as I said, is subtract row minimum. Okay, so I'll subtract row minimum. Identify each row. For example, first row now of a minimization problem. First row, the numbers are 9, 1, 0, 19 and 12. What is the lowest number? 0. Fine. Subtract the lowest number from all numbers of that row. That means subtract 0 from all numbers of that row. That means what? Don't do anything. Subtract 0 means don't do anything. So copy the first row as it is. So okay, fine. 9, 1, 0, 19, 12. Second row. Identify the lowest number. The lowest number in the second row is 3 or this 3. Subtract 3 from all numbers of the second row. Fine. So how do we do it? 3 minus 3, 0. 17 minus 3, 14. 14 minus 3, 11. 3 minus 3, 0. 8 minus 3, 5. Can you see, and you must have guessed that this, we are going to get a 0 in each row. Obviously, if I subtract the row minimum, in each row there will be a 0. Fine. Third row. Third row also I have a 0. That means there is no need to do anything. Third row is copied because I won't be subtracting 0 from all numbers of that row. Obviously, I'll get the same numbers. So I'll copy the third row as it is. So 1, 13, 8, 0, 1. Fine. Third row dealt with. Fourth row. What is the minimum number in the fourth row? Minimum number in the fourth row is 5. So subtract 5 from all numbers of the fourth row. Fine. So 8 minus 5, 20 minus 5, 11 minus 5, 5 minus 5 and 6 minus 5. Okay. I got the fourth row. Fifth row. What is the lowest number in the fifth row? It is 1. So subtract 1 from all the numbers of the fifth row. So what do I get? Each number is reduced by 1. So this is 0, 4, 3, 4, 1. So what do you find? Row minimum has been subtracted from all numbers, from all the rows, the row minimum has been subtracted. As a result, what has happened? In each row, there is at least one 0. Here there is a 0, here there are 0, 0 here, 0 here, 0 here. Fine. So row minimum subtracted. Now next step, subtract column minimum. Now as you will see, some of the columns already have a 0. So there is no need really to do anything. For example, column number 1 has 2 zeros. So there is no need to do anything in column number 1. There is, the minimum number is already 0. Second column, the minimum number is 1. That means I'll have to subtract 1 from all numbers of the second column. Third column, there is already a 0. Fourth column, there are already zeros. So there is no need to do anything in respect of third and fourth column. And the fifth column, there is no 0. The minimum number is 1. I'll have to subtract 1 from all numbers of the fifth column. So which we'll do now. So I get the new matrix. Now remember, this matrix is of no use for the time being. I'll remove this. We have already converted the problem into minimization and we are solving it. I'm keeping this matrix because this is going to be required at the end. Okay, fine. Now look at this. First column, I said nothing is required to be done, so I'll copy the first column. Now remember, we are dealing with the matrix column by column. First we dealt with the matrix row by row. Row by row when I dealt with, I got each row to have at least 1 0. Now column by column when I do it, I'll have at least 1 0 in each column. Column number 1 already has zeros, so there is no need to do anything. So I'm copying column number 1. 9 0 1 8 0. Fine. Second column, the lowest number is 1. That means I'll be subtracting 1 from all the numbers of the second column. So subtract 1, easy calculation. This does not require a calculator. So this is 13, 12, 14, 3. Now is there a 0 in the second column? The answer is yes, there is a 0 in the second column. Okay. Third column, there is already a 0. I don't have to do anything. Same situation with the fourth column, there are already zeros. So third and fourth column, I'll be copying as they appear. Okay. So third column, 0, 11, 8, 6, 3. Fourth column, already zeros are there. So 19, 0, 0, 0, 4. Fifth column does not have a 0. The lowest number in the fifth column is 1. So I'll be subtracting 1 from all the numbers of the fifth column. Can you see there will be 3 zeros in the last column now? Where 3 numbers are 1. If I subtract 1 from all these numbers, there are going to be 3 zeros in the last column. Okay. So subtract 1 from all the numbers. 11, 4, 0, 0, 0. Fine. After doing this second step, that means after subtracting column minimum, do you see that in each row there is a 0, in each column there is a 0. Once we are convinced that in each row and each column there is a 0, we can go to the next step. What is the next step? Try assigning. Try assigning. Try assigning. Make an assignment. That means decide which salesman will go to which district. I may succeed in this assignment, I may not succeed in this assignment. Okay. Now see, the procedure given in your study notes is somewhat different, and we follow a systematic approach whereby the objective is now to draw minimum number of lines through this matrix, either vertical or horizontal, in such a way that all the zeros are cancelled by a line. Either there is a vertical line or a horizontal line through each and every zero of the matrix. How many zeros are there in the matrix? Just see. I have to draw lines to cancel all the zeros. Now before that, we'll try to make an assignment. Trying to make an assignment, when I say, obviously when I am saying trying to make an assignment, there are two outcomes expected. I may be successful, I may not be successful. Fine. So what do we do? How to make an assignment? Making an assignment is not a matter of guesswork. We have to make an assignment at a 0 which is unique. What is a unique 0? A 0 should be unique either in the row in which it is present or in the column in which it is present. The 0 should be unique either in the row or in the column. Fine. We make an assignment at that 0. Now since the idea is to get one salesman for one district, if I make one assignment in that row or in that column, there cannot be any more assignment. Fine. Let's see how to do it. Now what we follow is a structured approach. Structured approach means a systematic approach where we examine the matrix from top to bottom and from left to right. We examine each and every 0. What do? We examine each and every 0. Let me begin with an example here. See now, say I start in the first row because I am starting from left to right, top to bottom. This is the first 0 which I will see. Stop at this 0, examine whether this 0 is unique in the row. The answer is no because of this 0. Is it unique in the column? Yes, it is unique in the column. If it is a unique 0 either in the row or in the column, we make an assignment. In other words, what I am proposing is salesman S1 to district D2, I am deciding an assignment. Remember always, I may be successful, I may not be successful. When can I say I am successful? If I am able to get 5 assignments, then I am successful. If I am not able to get 5 assignments, then I have to go to iteration number 1. So we are on step number 3, trying to make an assignment. Okay. Now what has happened? I have decided tentatively that salesman S1 be assigned to district D2. That means salesman S1 cannot be assigned to any other district, or district D2 cannot have any other salesman assigned to it, which means that if I have an assignment already made, any other 0 in that row or in that column is of no use for making an assignment, and therefore will cancel them. So this 0 is cancelled. That means I cannot make an assignment at this particular 0. Fine. Now this 0, first row, the zeros are finished. 1 0 I made an assignment, second 0 I cancelled. Then I go to the second row. Is this 0 unique in the row? The answer is no because of this. Is it unique in the column? No, the answer is no because of this 0. So this 0 is not unique. I cannot make an assignment at this 0 at this stage. Okay. Next, I see this 0 next. Is it unique in the row? No, because of this. Is it unique in the column? No, because of this. So I cannot make an assignment. Fine. So row number 2, I cannot make an assignment as of now. Row number 3, I come here. This 0 is not unique because of this and this. So this 0 is not unique in the row or column. I cannot make an assignment. This 0 is similarly not unique because of this and this and this. So I cannot make an assignment. So 3 rows, row number 3, I cannot make an assignment. Row number 4. Row number 4, I go, I find this is the first 0. This is not unique because there are zeros above it. There are zeros to the right of this. This is not unique. This is not unique. Okay. Next, this 0. Is it unique in the row or column? No, the answer is no. Because of this, this is not unique in the column. Because of this, it is not unique in the row. So I cannot make an assignment as of now. This 0 also I cannot make an assignment because it is not unique. In other words, there was only one unique 0. I made an assignment. Now unique zeros are over. No 0 is unique. Then what do we do? Then we go to non-unique zeros. Okay. First, examine whether unique zeros are available. Unique zeros are not available. Therefore, we go to non-unique zeros. Once again, we start in the same way. Go to the top of the matrix, left to right, top to bottom. Which is the 0 which I will see first? This is the first 0 which I will see. Fine. So this 0 I am saying, this is not unique 0, but since unique zeros are over, now I am making assignment at non-unique zeros. Therefore, I will make an assignment here. Okay, I made an assignment. Obviously, other zeros in this row or column have no use now. Therefore, I need to cancel them. I cannot have an assignment here because it is in the same row. I cannot have an assignment here because it is in the same column. So I remove this. Okay. Examine similarly. Now, it is quite possible that when you make an assignment at a non-unique 0 and cancel the remaining zeros in that row or column, it is quite possible that some other 0 may become unique. For example, now see, because this 0 is cancelled, this 0 has become unique in the row. So unique 0 always gets first priority. So unique 0, we must make an assignment. So I am making an assignment here. That means what I am proposing is salesman S5 to district D5, I am making an assignment. The reason being, unique zeros were over. I went to one non-unique 0. I made an assignment, and because I cancelled this 0, this became unique, so I made an assignment. Now since I have made an assignment here, other zeros in this column or row have no use. So this is already cancelled. The other zeros in this column are of no use. So this stands cancelled, this stands cancelled. So I got in the process so far 3 assignments. Are any zeros remaining? Yes, 2 zeros are still remaining. Is any one of them unique? I examine once again from top to bottom, left to right. The first 0 which I will see is here. Now look at this 0. Is it unique in the row? Yes, because this is cancelled now. So this has become unique in the row. So I must make an assignment here. So I make an assignment. But there is another 0 in this column that needs to be cancelled. So cancel this. Are all the zeros over? Yes, all the zeros are over. How many assignments we got? Only 4 assignments we got. That means our attempt was not successful. Try making an assignment, not successful. Unsuccessful. Okay, go into iteration number 1. What are the steps in iteration number 1? I'll write here. Firstly, I'll write the steps. Now see, what is the purpose of these steps? The purpose of these steps is to draw minimum number of vertical or horizontal lines through this matrix in such a way that all zeros, whether assignments are there or not assignments are there, all the zeros will stand cancelled. Fine. So how do we proceed? There is a systematic procedure which is laid down in many books. Unfortunately, your study notes do not cover these steps. So if you master these steps, I'm sure you will be able to solve any assignment problem on the earth. Okay, so long as it is manually manageable. For example, you can go up to 7 by 7 problem, or for that matter even an 8 by 8 problem. It is possible to solve, but as the size of the matrix increases, it becomes more and more difficult to do it manually. Okay. Now since I have not got the required 6 assignment, I go to iteration number 1. Now what are the steps in iteration number 1? I am calling it iteration number 1. The reason is I do not know whether there is going to be iteration number 2, because even iteration number 1 may not be successful. If iteration number 1 is not successful, I repeat the steps. I go to iteration number 2 till when? Till I get 5 required assignments. So iteration number 1. This iteration number 1 starts with the following steps. The purpose of these steps is to draw minimum number of lines. So I'll say steps to draw minimum lines. Line should be vertical, no diagonal line is permitted, remember. Draw steps to draw minimum number of lines. Okay. Now when do we do this? When we don't get required number of assignments. The required number of assignments here is 5. I got only 4 assignments, therefore I have to do iteration number 1. Now iteration number 1, firstly the steps to draw minimum number of lines is what we are looking at. Okay. Step number 1, tick the rows having no assignment. Okay. Next step, tick the columns. I'll write the steps first and then explain. Tick the columns having zeros. Tick the rows having no assignment. Tick the columns having zeros in the ticked rows. Okay. Step number 3, tick the rows having assignments in ticked columns. And step number 4 is simple. Step number 4 says go back to step 2 and 3 till no more ticking is possible. Keep on going to step number 2 and 3 repeatedly till no more ticking is possible, either of the rows or of the columns. Fine. Step number 5, the last step. Draw lines through ticked columns and unticked rows. These 5 steps will ensure. Now see, in the beginning these 5 steps look to be too much to do, but it is not actually. It's a matter of practice. Now look at these steps as I am doing it. Okay. What is the first step? Tick the rows having no assignment. Obviously, since we did not get 5 assignment, there will be at least one row where there is no assignment. Which row doesn't have an assignment? Row number 4 does not have an assignment. Okay. So tick the row having no assignment. Row number 4 is ticked. Okay. Only one row didn't have an assignment, so I ticked only one row. Step number 2. Tick the columns having zeros in the ticked rows. Okay. Are there zeros in the ticked rows? Obviously there will be zeros in the ticked rows. There are 2 zeros in the ticked rows. Okay. Tick the columns which have zeros in the ticked row. This is the ticked row. I am looking at only ticked row now. In the ticked row, whatever are the zeros, these are 2 zeros. So tick these columns, tick these 2 columns which have zeros in the ticked row. So 2 columns got ticked. Tick the columns having zeros in the ticked rows. So I did this. Step number 3. Tick the rows having assignments in the ticked columns. What are the ticked columns? These are ticked columns. Are there assignments in the ticked columns? Yes. In this ticked column, this is an assignment. Correct? So tick the row which is having an assignment in the ticked column. Examine this ticked column. Is there an assignment here? Yes, this is an assignment in the ticked column. Tick the row having assignment in the ticked column. Okay, step number 4 is over. Step number 3 is over. Tick the rows having assignments in the tick column. Now what does step number 4 say? Step number 4 says go back to step number 2 and 3 till no more ticking is possible. So I have to go back to step number 2. What is step number 2? Step number 2 says tick the columns having zeros in the ticked rows. How many ticked rows are there now? There are 3 ticked rows. 1, 2 and 3. What are the zeros in the ticked rows? Which zeros are present in the ticked rows? This is a 0, this is a 0. The columns are already ticked. This is a ticked row. What are the zeros in the ticked row? These 2 zeros are there in the ticked row. The columns are already ticked. Third ticked row. This is a ticked row. What are the zeros in the ticked row? This and this. This column is already ticked. but this column is not ticked. Therefore, I need to tick this column. So step number 2 had to be repeated. If step number 2 had to be repeated, obviously step number 3 will also have to be repeated, because step number 3 is based on step number 2. Now what is step number 3? Tick the rows having assignments in the tick columns. What are the tick columns? 1, 2 and 3 are tick columns. In this column, is there an assignment? Yes, the row is already ticked. In this column, which is a tick column, is there an assignment? Yes, the row is already ticked. In this ticked column, is there an assignment? Yes, there is an assignment. Is this row ticked? Not yet. So I need to tick this row. Okay. So step number 2 and 3 were repeated. Step number 4 says go back to step number 2 and 3 till no more ticking is possible. So let's examine step number 2 and 3 once again. Step number 2. Tick the columns having zeros in the ticked rows. Okay. Zeros in the ticked rows. How many ticked rows are there? 1, 2, 3, 4. What are the zeros in the ticked rows? In this row, these 2 are zeros. The columns are already ticked. In this ticked row, these 2 are zeros. Columns are already ticked. In this ticked row, these 2 are zeros. Columns are already ticked. And in this ticked row, these 2 are zeros and columns are already ticked. That means no more ticking is possible. So ticking procedure is over. Step number 4 says go back to step number 2 and 3 till no more ticking is possible. Now we can see that no more ticking is possible. So what do we do? Step number 5. Draw lines through ticked columns and unticked rows. Okay. Draw lines through ticked columns. How many ticked columns are there? 2 ticked columns are there. Fine. So draw lines through ticked columns. 3 vertical lines, ticked columns. Draw lines through ticked columns and unticked rows. How many unticked rows are there? Only one unticked row is there. Only the first row has not been ticked. All other rows have already received a tick. In other words, unticked row is only 1. So horizontal line is only 1 and vertical lines will be 3. In other words, 3 vertical and 1 horizontal line will make it totally 4 lines. And 4 lines will be able to cancel all the zeros in this matrix. So how to do it? Draw lines through ticked columns. Okay. Ticked column, ticked column, ticked column. Draw lines through ticked columns. Done. Draw lines through unticked rows. There is only one unticked row. First row is unticked. So draw a line through unticked rows. What do you see? Have we got a line passing through each and every zero? Yes. All the zeros in the matrix are cancelled by one line, either vertical or horizontal. Sometimes it could be 2, one vertical and one horizontal. So this is the new matrix. How many lines did we require to do this? Cancel all the zeros? Only 4 lines. It will always be less than the size of the matrix. The very fact that we could not get 5 assignments in our first attempt means that the number of lines required is not going to be 5, it is going to be less than 5. It could be 4, at the most 4. It could even be 3 and 2. Fine. So this is this step. What are the purpose of these steps? To draw minimum number of lines, vertical or horizontal. We have drawn 3 vertical and 1 horizontal line, cancelling all the zeros, and therefore this is the new matrix on hand. Now what is the next step? Identify the lowest value. Okay, fine. So now see, if you can observe this matrix, there are 3 types of basic elements in this matrix. Some elements have no lines passing through them. For example, these 8 elements, no lines are passing through them. There are 3 intersections here, one vertical, one horizontal line, where 2 lines are passing, one vertical and one horizontal. That means there are 3 elements where there is an intersection. And what are the remaining elements? The remaining elements are such that there is only one line passing through them. There is only one line. For example, this element, only one line is passing, only one line is passing, only one line is passing, only one line is passing. But here, there are 2 lines passing through this, one vertical and one horizontal. So 3 types of elements are treated in 3 different ways. Okay. Now, what is the procedure? Mark the procedure. Look at the elements which have no lines passing through them. These are the elements from which no lines are passing. These 8 elements here are such that no lines are passing through them. So pick up the lowest out of this. Now if you see all these numbers, the lowest value is 3. Okay. So 3 is an important element for this iteration now. Iteration number 1, we are on iteration number 1. Because our initial attempt failed, we are on iteration number 1. So how to proceed? Now look at the 3 types of elements. What are the 3 types of elements? Some elements only one line is passing. Some elements 2 lines are passing. And some elements no lines are passing. Okay. Concentrate on the elements on which no lines are passing. The number of elements on which no lines are passing, from which no lines are passing is 8. Subtract this lowest value 3 from all these 8 elements. So all these 8 elements, I'll be subtracting 3. Okay. What do we do at the intersections? At the intersections, we add the same number, that is 3. How many intersections are there here? 3 intersections are there. One is 9, one is 19, one is 11. We'll be adding 3 to these numbers. Fine. What do we do where there is only one line passing through the element? For example, only one line is passing from here or here, 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 here. Only one line is passing. We don't change this element in any way. Fine. Good. So, obtain the next matrix. How do we obtain the next matrix? Element at the intersection. So, we add 3. Next 2 elements, one line is passing. When one line is passing, no change is required. Again, element at the intersection, add 3. Again, element at the intersection, add 3. So I'll be adding 3 basically in the first row at 1, 2 and 3 places. And where there is only one line, I am not making any change. Where there is one line, we do not make any change. So what are the new numbers? Let me write down the new numbers. 9 will become 12. 0, 0, only one line is passing, so no change. 19 is an intersection, so I'll add 3. 11 is at an intersection, so I'll add 3. 11 plus 3, 14. Now I go to the second row. In the second row, the first element has only one line passing through it, so no change is called for. Second and third element have no lines passing through them. When there are no lines passing through the element, we'll subtract 3. So 13 minus 3, 10, 11 minus 3, 8, and then one line, that means no change, 0 and 4. Fine. Third row. Can you see similar situation in the third, fourth and fifth row? First element, no change. Next 2 elements, subtract 3. Next 2 elements don't make any change because only one line is passing through them. So 1 remains 1. 12 becomes 9, subtract 3, 8 becomes 5, subtract 3, 0, 0, no change. So third row is dealt with. Fourth row, 8. One line is passing, no change. 14 minus 3, 11. 6 minus 3, 3. 0, 0, unchanged because one line is passing through them. Last row, first element, one line is passing, so no change. Next 2 elements, no lines are passing, throw 0, 0. Next two elements, one line is passing, so no change, 4 and 0. This is the new matrix, which means now I should try once again to make assignments, firstly at unique zeros, and once unique zeros are over, we should make assignment at non-unique zeros. How do we follow the procedure? Top to bottom, left to right. Identify a unique 0 starting from the first row. Let me go to the first row. Is this 0 unique in the row? No. Is it unique in the column? No. So I cannot make an assignment right now. Same situation here. Not unique in the row, not unique in the column. First row, I cannot make an assignment. Second row. This 0 is not unique because of this and this, so I cannot make an assignment. Obviously, this 0 is not unique because of this and these, so I cannot make an assignment. Row number 3. These 2 zeros are not unique because of these and these. This is not unique because of this, and this is not unique because of this and this. So I cannot make an assignment in the third row. Fourth row, what is the situation? Again, this is not unique, this is not unique in the row or column. It should be unique either in the row or in the column. Any one will do. Fifth row. Is this 0 unique? No. Is this 0 unique? Not in the row, not in the column because the top line 0 here. This is not unique. and this is not unique. In other words, unique zeros are over. We could not make a single assignment because unique zeros were not there. So after unique zeros are over, what do? We go to non-unique zeros. Again, start from top to bottom, left to right. We follow the structured approach so that we should not go randomly, fishing around in the matrix. We should go in a particular sequence of steps. So first row, I have convinced myself that there are no unique zeros. So now I am going to make assignment at non-unique zeros. Fine. So this is the first zero which I say it is not unique, that we have already seen, but I am making an assignment here because there are no unique zeros. So I make an assignment here. What is the next thing? If an assignment is made, there cannot be any other assignment in that row or in that column. So other zeros in that row or column need to be cancelled. So I cancel this zero and I cancel this zero because it is in the same column. I cancel this zero because it is in the same row. Examine, after cancelling some of the zeros, some other unique zeros may emerge. Can you see that when I cancelled this zero, this became unique in the column because this zero is cancelled. This became unique in the column. So I'll make an assignment here first. First priority always make assignment at unique zero. So I make an assignment here. Now when I make an assignment here, this zero is unique in the column. My objective is always to make an assignment at a unique zero first. I made an assignment at a unique zero. This zero became unique when I cancelled this. So I made an assignment here. But other zeros in this row now are of no use. So I cancel this and this. Fine. Now does cancellation over here at these two zeros make any other zero unique in the row or column? The answer is yes. This zero now became unique in the column because there is no other zero in this column. Because I cancelled this zero became unique in the column. So I must make an assignment here first. And since I made an assignment, there cannot be any other assignment here. So I cancel this. Fine. Once again see, unique zeros are over. They became unique later on, but we made assignment there. Now these four zeros are such that they make each other non-unique. So unique zeros are over, only non-unique zeros are available. So we make assignment now at non-unique zeros once again. Go from top to bottom, left to right. Which is the first zero which I will see? This is the first zero which I will see. So I make an assignment here. When I make an assignment, what happens? There are two zeros, one in this row and one in this column. They are of no use, so I cancel those. No assignment is possible here and here. Now is there any zero left? Yes. Is it unique? Yes, now it is unique both in the rows and column. So I make an assignment. Fine. So count the number of assignments. I got the required number of assignments, that is 5. The moment I get the required 5 assignments, the problem is over. I have solved the problem. But remember, did we make assignment at non-unique zeros? Yes. In fact, we started with a non-unique zero. Therefore, when you make assignment at a non-unique zero, which was the first assignment at a non-unique zero that we made? This was the first zero in the first row where we made assignment at a non-unique zero. If I made assignment here, instead of that, supposing I had made it here, then I had to cancel this and then I had to cancel this. That means the assignments would have been different. In other words, if you make assignment at non-unique zeros, there is a possibility that the question will have multiple answers. Now, if you read the question in the book, it says that find at least one more solution. Find at least one more solution with the same cells level. Fine, we'll do that, but 5 assignments have been obtained. What are the 5 assignments that we are proposing? We are proposing that salesman S1 will go to district D2, salesman S2 will go to district D1, salesman S3 will go to district D4, salesman S4 will go to district D5, and salesman S5 will go to district D3. As you can see, each district has only one salesman associated with it, and each salesman is associated with only one district. Therefore, this is the 1:1 assignment. The algorithm itself is that it should be a 1:1 assignment. What happened? There were 120 ways of making assignment. We directly obtained the optimal assignment. Now, what are the cells? The cells will be what the numbers stand for. Now, for example, S1 is allocated to district D2. Which is the number? This is the number. Salesman S1 allocated to district D2. Second row, where is the assignment? S2 is allocated to district D1. That means this is the assignment. Salesman S3, where is the assignment? In the fourth place in row number 3. What is the fourth place in row number 3? This is the one. Can you see? We made assignment where the sales are maximum, at least one of them. 49. I said we would like to make an assignment here if it is possible. So S3 is allocated in D4. What about S4? S4, if you see the fourth row, the assignment is in district 5. That means S4, district 5. And S5 goes to salesman S5 goes to district number 3. That is, this is the assignment. Fine. Now this is the total sales which can be obtained. 48 plus 46 plus 49 plus 43 plus 45. Okay. We'll total this up, but we must write the solution in a structured manner. Okay. Now what is the structured manner? A systematic way of summarizing the solution that we have obtained. We got the solution fine, but we also know that there is a multiple solution. There can be multiple solutions when? When can the multiple solutions be there? When you made assignment at non-unique zeros, there can be multiple solutions. We'll find one more solution. Now for example, see, whatever the last two assignments, we made assignment here, then we cancelled these two, and therefore this became unique, and we made assignment here. So we made assignment at these two places and cancelled these two. What would be another way? Make assignment at these two and cancel these two zeros. Correct? So that would be another solution. Fine. So now let's write down the solution in a structured manner. Salesman, district. Let's write down the names of all the salesmen: S1, S2, S3, S4, S5. These are the various salesmen. What are the districts which we have allocated to them? Salesman S1 is allocated to district D2. What are the cells? 48. Salesman S2, where is he assigned? To district D1. What is the cell possible? 46,000. Okay. Salesman S3 assigned to district D4. S3 assigned to D4. What is the possible cell? 49. Salesman S4, where is he assigned? District D5. Salesman S4 assigned to district D5. What are the possible cells? 43. 43 means 43,000. Next, S5 assigned to D3. What are the possible cells? D3. The possible cells are 45. So this is the total cell which I can get, and this cell will be maximum. I cannot make assignment in any other way and get more cells than this. But what is the total? 231. Which means that we can get maximum cell of only 231,000, that is 2,31,000. Making assignment in any different way will not be able to give us as many cells, but there are multiple solutions as we observed. That means the cell will remain 231, but there will be at least one more different way of making assignment where the cells will remain same, but the assignments may be totally different. Okay, so let's find out that solution as well. Okay. I am rewriting the matrix with which we got these 5 assignments. The matrix I'll rewrite. The previous steps have already been gone through. Required number of 4 lines were drawn. After drawing 4 lines, what did we do? We drew 3 vertical, 1 horizontal line that resulted in cancellation of all the zeros. Remember, there were 3 types of elements there. What are the 3 types of elements? Elements with no line, elements with 1 line, elements with 2 lines. How do we deal with them? Elements with no lines. Find out the lowest value, which was 3. We subtracted 3 from all the elements which had no lines. Okay. Elements with 1 line. What do? We don't do anything. We keep them as it is. And elements with 2 lines. When is it possible to get elements with 2 lines? 1 vertical and 1 horizontal line. In the first row itself, we had got 3 elements which were at the intersection of a vertical and horizontal line. There we added 3. Okay, fine. So this is the matrix that we had obtained. I am trying to show you how one more assignment is possible, or in fact more than one assignment is going to be possible. Fine. Third row, 19500, 195. I am simply copying this matrix. I am not doing anything. All that has been already done. 8, 11, 3, 0, 0. Then 0, 0, 0, 4, 0. This was the matrix. When I made assignment, I started with this matrix and I successfully got 5 assignments. Now we started where? Since there were no unique zeros, we said we'll start at non-unique zeros. Which was the non-unique zero with which we started making the first assignment? This was the non-unique zero where I made the first assignment S1D2. Now instead of this, I will change it. I'll make an assignment here. Okay. So if I make an assignment here, see what happens. That means I am assigning salesman S1 to district D3, not D2. Now what happens when I make an assignment here? Other zeros, row and column need to be cancelled. So I'll cancel this 0. I'll cancel this 0. Watch out. If you cancel some of the zeros, some other zeros may become unique. Can you see that this 0 has become unique? Because this is cancelled, now this becomes unique. So I must first make an assignment here. So I'll make an assignment here. First priority always unique 0. After unique zeros are exhausted, only then we can go to non-unique zeros. Now since I made an assignment here, I need to cancel this 0 and this 0 because they are in the same row. Fine. There is no other 0 in this column because it is already cancelled. Now what happens? Has any other 0 become unique? Can you see that this 0 has become unique? The moment I cancelled this became unique in the column because there were 2 zeros in this column. One is cancelled, so this has become unique. So I make first assignment here. Unique 0 always gets my first priority. Then I need to cancel this. Fine. Now 3 assignments are already made. Zeros are not over. Can you see that these 4 zeros which were there in the previous attempt also, we had these 4 zeros remaining and we made the last 2 assignments. Which were the 2 assignments which we made? We made assignment here and we cancelled this. What is the other way of doing it? We can make assignment here and cancel this. Both are fine, but that will be yet another solution. So I make assignment as before at this 0, cancel this and this, and at this 0, no other 0 is required to be cancelled. So what is the new solution? This is a new solution. Assignments are different than the previous one. But are the cells same? As I said, yes, they should remain same. So let's just jot down. Now see, the other districts. What is another possibility? Solution, this is district, solution number 1, solution number 2. What is the solution? Now see, S1 goes to D3, S1 goes to D3. What are the cells? S1 goes to D3. What are the resulting cells? 49. Okay. S2 goes to D1, S2 goes to D1, 46. Then S3 goes to D4, S3 goes to D4, 49. S4 goes to D5, S4 goes to D5. What are the cells? 43. And S5, S5 where does it go? District D2. What are the cells in district D2? 44. District D2. Possible cells are 44. Total of this. Again 231. What we said is we'll get another solution with the same cells level. The question clearly says find one more solution with the same cells level. Now see what is the difference between these two. See, this assignment is D1, this assignment is D1. This is D4, this is D4. This is D5, this is D5. But what is the difference? This is D2, this is D3 and this is D3, this is D2. Assignment is different. What is another way? Changing these two. This can be any other way. Okay. Now for example, this can be here and this can be here. These two will be cancelled and these two will be assignment. Another solution. In fact, we have got 4 solutions here. But what is the cells level? Cells level remains same at 231. So the structured way to write down the solution is this. In fact, this was the shortcut for writing another solution. So I have made 2 columns here and 2 columns here. But individually, if we write it separately, the cells remain same at 2,31,000 and we get 2 different answers for the same question. When do we get 2 different answers for the same question? When we make assignment at non-unique zeros, we get different answers. And therefore, this is called as a multiple solution or alternative solution or an additional solution. Okay, this is a totally different solution than the one which we opted. But this results in the same cells level. As I said, in any other way, you cannot get more than 2,31,000 rupees of cells. But for getting 2,31,000 rupees of sales, there are not 1, 2, but there are 4 solutions which you can obtain yourself. I have obtained 2 solutions. How do you obtain 2 more solutions? Change this to this, either in the first solution or second solution, both. You can change these 2 to these 2 and you have another solution. 2 more solutions are possible. So this is the way to solve an assignment problem. And with that, we have successfully solved the first assignment problem. To recollect, what did we do? We did the pre-checks. What were the pre-checks? First, check if the problem is a minimization problem. It was not a minimization problem. We converted the maximization matrix into minimization. How did we do it? We subtracted all the numbers from the highest number in the matrix. The highest number in the matrix was 49. Therefore, we subtracted all the elements from 49. We obtained a new matrix. We solved actually that matrix, not this matrix. We are getting solution to this matrix through that minimization matrix. Okay, fine. So that was the first thing. Then we checked whether it's a balanced problem. Fortunately, this problem was balanced. When do we say the problem is balanced? When there are 5 rows and 5 columns, number of resources, number of users is same. So it's a balanced problem. We didn't have to do anything to balance it. So we proceeded. The pre-checks, one was unsuccessful, one was successful. Unsuccessful one was minimization. We converted into minimization, then proceeded to the next check. Next check was successful. Then we applied the steps of Hungarian assignment problem. That means subtracted row minimum, subtracted column minimum. After doing this, we got a 0 in each row and each column. We tried to make an assignment. We failed. We could not get 5 assignments. We could get only 4. Therefore, I said now we must go to iteration number 1. What was iteration number 1? What is the first part of iteration number 1? Draw minimum vertical and horizontal lines passing through these 5 steps. Okay, we'll revise these steps again and again. See, crux of assignment problem is really revising these 5 steps and having enough practice on these 5 steps. If you can get practice on these 5 steps, no assignment problem is different. We'll take some of the very difficult problems also in this class.